Alright, so concave mirror is the one that is curved in, and it has a focal point where all the parallel light rays, these guys that are parallel to the principal axis, focus together. So that's why it's called a focal point. The focal length is half of the radius, so C is where you would put your compass needle to draw the circle. So this is radius, that's the focal length, which is exactly half of it. Focal length with this type of mirror is positive because you can touch it with your fingers right there. You are here, that's the real world, this is the virtual world, this is behind the mirror. So how do you draw? There are several cases for this particular mirror because your image actually changes depending on how close the object gets to that mirror. So let's start with where the object is far away, longer than the radius. There are three types of rays altogether. The first one, if it comes in parallel, you will continue it, bounce it off of the mirror through the focal point. That's the first one. The second one comes through the focal point, bounces back parallel. And there's a third one that goes through the center, through the radius, and semi in the same place that will cross. If you do it with a pencil and a ruler, that will be more accurate. But here's where you will get your image, because you were gathering information on the tip of the arrow, and that's where it will, all those three light rays will meet, and that's where the tip of your arrow will be. So what you see here, here's your image. It's flipped, which means it's real, inverted, and the size is smaller. That's when your object is far away, farther than the center of the curvature, so basically longer than radius. If your distance to the object from the object to the mirror is longer than the radius, you're going to get a real, inverted, and smaller image. Now, if you have your object closer, so between the radius and the focal point, the focal length for that matter, again, you're going to use two light rays. You can use three, but two is enough. So parallel through focal, parallel, that's where they met, so that is your image right here. As you see, it's still real because it's flipped. So it's still real inverted, but now it's bigger. And then at the focal point, if your object is at the focal point, I'm going to use two light rays. I cannot draw a light ray that goes through focal and the tip. So I'm going to use the third one technically, the one that goes through the center of curvature. It will bounce back the same way. And as you see, the two reflected light rays, this guy is reflected and that guy is reflected. They are parallel, which means that you will not get an image if your object is at the focal point. Now once you pass the focal point, what you're going to see is a bigger image, and it's going to be virtual, and here's how it's formed. Again, you're going to go parallel through the focal point. You can technically go through the focal point tip, but I don't have enough mirror to reflect it, so I'm just going to go for the center again. Bounces back the same way. As you can see, they're not going to cross in the real world. That means that you're not going to get a real image. So I cannot put a screen in the real world and get the reflection. So what your brain does for you, it extends the light rays that were reflected. So here's the extension of the one that went through the center, and here's the extension that reflected off of the focal point. So the place where they do meet in your brain, it's not a real image, this is just your imagination, because that your brain is doing that work for you. This is where the tip of the arrow will be, and your image in this case is going to be virtual, upright, and bigger. So again, if your object seems upside down, or like if you see it upside down, that means it's a real image and it's flipped. And the size could be bigger or smaller, but if it's an upright image, it's virtual, it doesn't exist, it's all in your brain. So here's all the stuff for the concave mirror. It will give you real images. It can be a smaller or bigger depending on where you are, but once you cross the focal point and get closer than the focal length, which is half of the radius, your object will be virtual, upright, and bigger. Now, distance to the actual real image is going to be positive, but if it's a virtual image, your distance to the image is going to be a negative. Magnification, which is the ratio of heights, it's going to be less than 1. It's going to be positive and less than 1. I mean, it's going to be negative actually, because it's flipped. Magnification is height over height, height of the image over height of the object. If your image is flipped, the height is technically negative because it's pointing down. So negative magnification for real images. Smaller, so height of the image is smaller than the object, height of the image is bigger than the object. So for example, if you have a real image which is smaller, your magnification can be negative 0.5. If you have a real image but bigger, your magnification could be negative 5. So your image is 5.5, so half of what it was, or 5 times greater. And then if it's a virtual image, your magnification is positive and it's more than 1 because it's always going to be bigger. So let's look at an example. You have a 45 centimeter, that's the height of the object, 45 centimeter object reflected upside down. So since it says that it's reflected upside down, you know two things. It's a real image and your magnification is negative. It appears only 15 centimeters in height, so therefore you have a smaller image. And your radius of curvature for that mirror is 20 centimeters. Remember that focal length is half of it, so focal length for this mirror is going to be 10 centimeters. So we need to find how far from the object the mirror is located. So you're figuring out DO, which is distance to the object. We have two formulas. The formula for magnification, that is again the ratio of heights, or negative ratio of distance to the image and distance to the object. You know your ratio of heights. Remember, it's a real image, so 15 centimeters is technically negative. So my magnification is negative 15 because it's flipped over 45. That gives me negative 1 over 3. So that is my magnification, which also equals negative di over dou. So from there, I can relocate and say that my di is 1/3 of dou. So I'm going to substitute di in the formula, which is 1 over f equals 1 over di plus 1 over dou. That's the regular formula, works for everything, just like this one. So I'm going to substitute di for dou. So since it's 1 over di, it's going to be flipped, and you're going to end up with 3 over dou. So 1 over dou plus 3 over dou equals 1 over f. 1 over f, again, radius is 20, which means that the focal length is 10, which is half, equals, when you do 1 plus 3 is 4, 4 over dou. From there, dou is 40 centimeters. And you can check yourself. It is greater than double the focal length. So it's definitely going to be a smaller image. So your distance to the object, or the distance between the object and the mirror, is 40 centimeters in this case.